Thanks, Jim. So I want to welcome you both to the center and all the activities, and as well as the retreat we will have next week. So you'll get a pretty good sense of our overall activity, and I urge you to participate actively in the boot camp next week. So today what I want to do is give you a sense of how we describe in a mathematical way as well as in a more conceptual way the different types of behaviors that the biological materials display. Okay, so you've had many courses, many lectures, and I'm sure you're familiar with linear elasticity. I'm sure that's a familiar concept. Basically, linear elasticity is stress proportional to strain. But there is no biomaterial that is linear elastic over a wide range. Almost any material you can think of, bio or non-bio, will deviate from linear elasticity. That's an approximation. So what we want to think about is what are the different types of behaviors that these materials display, and there's a list of those. Okay, and I think it's a more or less complete list. So today what I want to do is go through each one of these types of mechanical responses. And the goal is, number one, to understand the basic fundamental physics. Why you get this sort of a deviation, and what is characteristic of a certain class of material. All right, and then secondly, very cursory way, I'm going to look at the mathematics behind it also. Okay, so have questions, we can go about math, we can talk about that later. But I want to emphasize the physics aspects of it more. So the first type of material that is not linear elastic is called hyperelastic. How many of you have heard that term? 1, 2, yeah, 3, good. So it just means that it is non-linearly elastic, means it's not a straight line but rather a curve. So that's a simple concept. But then we have to understand where this nonlinearity comes from. It can come from many sources. So I'll touch upon that, particularly relevant for biological materials. Okay. So in a sense, this is like a linear elastic material, but it is non-linear, but there's no dissipation. Meaning you keep pulling material, taking the load out, you will basically go back and forth without any dissipation. Okay. All the other models that I'm going to talk about have dissipation in them, and almost any material is dissipative for various reasons, and we'll see what some of these reasons. Of course, you know from common knowledge that there is dissipation almost everywhere. All right. Okay, very good. So the second type of material that is that's material response called poroelastic. So poroelastic basically means a material has both a solid component and a fluid component. So there is water, which is everywhere, right? Significant percentage of a cell is water. Significant percentage of your body is water. I don't know, I think it's 75%. I think that's the number, is water. So then you have to account for two phases. So these poroelastic models are also called biphasic models. And the theory that describes this is called poroelasticity. Okay. And now there are also extensions of this called triphasic models, meaning in addition to the fluid and the solid component, you also have to account for floating charges. There are positive and negative charges. So that's triphasic, 3 phases. Okay. And then the next class of materials is viscoelastic, which is distinct from poroelastic in that the same material behaves as a solid and fluid. Poroelastic, there's a solid part, there's a fluid part. Viscoelastic is one material that's behaving both as a solid and a fluid. That's viscoelasticity. Okay. And then there is what's called plasticity. Plasticity is permanent damage or permanent deformation. When you pull something, take the load out, it doesn't return to where you started from. That's because there are some dissipative mechanisms in there that's preventing it from doing so. So that's plasticity. Distinct from plasticity is also you can accumulate damage. You might, you might deform a material and then take the load out. It'll come back to where you started from, but then there are a lot of defects in the material, and it is, its modulus is different. That's called, those models are called damage models. Okay. And finally, there are active material models, meaning These are things like muscle, cell, all of that they use ATP to convert chemical energy to mechanical energy. So any deformation also has to couple to phosphorylation of ATP and generation of energy. So chemical mechanical coupling, okay. So there's sort of external energy coming into your mechanical system. So these are these are the models. Now what I want to point out is these are really distinct model, which means mathematically if you write a relation between stress and strain, they are distinct for all these different models, okay. And they are actually idealizations, which means any real material you look at could be a mixture of these things. For instance, we will look at materials that are poro viscoelastic, meaning it has features of poroelasticity, it has features of viscoelasticity and elasticity. Similarly, viscoplastic, hyperporoelastic, active poroelastic, you can kind of mix and match if you will. All right, but then the fundamental thing is that it's these concepts one has to understand. All right, any questions so far? All right, very good. So let's see why one might want to do something like this. So I'm going to go through this very quickly. So so I'm looking at the elastogram, which is ultrasound images of liver, and this is a normal liver. You see the stiffness is of the order of about 2 kilopascal. And this is a fibrotic liver. You see the stiffness are much bigger. So the point is that in disease states, the mechanics or the elasticity of all of these materials change. All right. So it's important, really, the biology is really intimately connected in some sense to the mechanics. Okay. Same thing. If you look at metastasis of a cancer cell, yeah, this is responding a little bit slowly. Okay, so you see that this is your primary tumor. Cells have to escape from the tumor. They see like a fibrous environment around them. They have to then get into a blood vessel, go through the blood vessel, and form secondary colonies. All of this really involves a lot of mechanical processes. Cells have to move through a matrix. So really the mechanics of what's around it is important. And here the cells have to get into the blood vessel. So really the mechanics of the nucleus is important because you got to squeeze the nucleus through. Then there is flow. So mechanics is important everywhere. All right. And I'll skip this the next slide in the interest of time. The next 2 slides. I think it's best if I just use this. All right. So now I want to so clearly we want to understand the mechanical response of these different components. So just for a review, so linear elasticity is basically if you take a rod, say, and you stretch it, the stress is basically the force divided by the area. The strain is the change in length divided by the original length. And for many materials, you basically get a straight line. And the slope is called modulus of elasticity. Now I've given you numbers for different materials. Typically, in some limits, we'll come to those limits in a second. Biological materials are soft. They have a modulus about 10 to the 5 Pascal, which is like 10 kilopascal, if you will. Things like steel have 100 gigapascal, they're much stiff. So there's a range of these stiffnesses. Okay, so that's the ideal behavior. When you pull something, there has to be deformation, and the simple thing to assume is the deformation is proportional to the force. So that's linear elasticity. But now if you take a material like rubber, right? I mean, so rubber has been a material that has been studied because it's a lot of different applications. You plot the strain versus stress, this clearly doesn't look like a straight line. You see it's curved. All right, and the way it is curved in some senses, if you look over here, this segment that maybe looks like a straight line, this segment here looks like a straight line, but overall the whole thing is not a straight line. Okay, and I told you a second ago that the slope is the elastic modulus. So what this material is doing is it's actually a nonlinear material, but the slope is increasing, which means it's becoming stiffer and stiffer when you apply this deformation. Okay, and this phenomena is called strain stiffening. Simply as you apply more stress, the slope goes up. So that's really the idea. So that's rubber. But let's look at the biological materials. Maybe you saw this from Paul Jamney's talk. So biological materials, typically when I showed you that tumor microenvironment, there are a lot of fibrous networks there. Collagen So this extracellular matrix is all collagen. So that's collagen. Within the cell you have actin. There are intermediate filaments, fibrin you find in blood clots and so forth. So these are all some of the standard components of biological materials. And here what's being plotted is the strain versus the modulus. Modulus, remember, was the slope. So if the material is perfectly linear elastic, what should you see on this graph? What kind of a curve should you see on the graph? What is it, Abby? Horizontal line. And that's what polyacrylamide is. I think some of you made polyacrylamide gels. It's a straight line. So that material is actually perfectly elastic. Okay? But many of the other materials, collagen, actin, fibrin, all of them strain stiffen, as you can see. Okay, meaning they become stiffer with deformation. So now next what I want to do is I want to understand why. I want you to explain why that's happening. Okay, and so nonlinearity is something to be expected. So why do you think something like collagen is stiffening when you apply more deformation? Yeah, that may be a method of stiffening in some materials. But collagen, it's a different mechanism. But that's a bona fide way some of the things like rubbers stiffen. Collagen is a different mechanism. So that's a very good point. There are many mechanisms. I'm just going to go through one. Okay. So let's look at collagen. So this really is the stress-strain response of collagen. That is strain, that's stress. You see, there is a toe region, meaning there is a region below, below which it's actually quite soft. That's the stress, that's a strain. Then it sort of more or less gives a linear response. Then eventually you pull it a lot. Anything you apply, you pull the heck out of it, it's going to break. So that's failure. It gets soft eventually. So what I want to understand is, why do you get this kind of a nonlinearity? Why does it start from being soft and then stiff? Okay. So the way we do this is, this is a computational model that one of the former postdocs in my group developed. So collagen is basically just a network of filaments. Okay. So these are all the filaments that you're seeing, and they are cross-linked. So it's just take a filament, cross-link it to the other, and just form a network. Each of these filaments is linear elastic, meaning if I pull it, you will basically get a linear elastic law. But also the filaments can also bend. So you can do, if you have a filament, I can do two things. I can bend it, I can stretch it, which is easier to do. If I have a filament, is it easier to bend? Bending is easy. So matter of fact, this nonlinearity, I'm going to tell you right off the bat, arises because of this competition between bending and stretching. Okay, so everywhere you see these links, they're all rigidly cross-linked. So cross-link dynamics, what's your name? Alex. So as Alex pointed out, cross-link dynamics is important, but you don't need it. It's important. I have a slide. You can get the nonlinearity without cross-link. Cross-links are rigid. There's no dynamics to them. Yet you can get nonlinearity. So to see that, let me just, it says cannot play media. It may be because this is an older slide. Yeah, it was movie was quite important, but let me just skip that and maybe show you what the data is. So the thing is, as you start deforming this material, you know what? I can pull up that movie real quick. All right, here. Oh, you can't play that either. You know what, the thing is, I bought this computer like less than a month ago, and a lot of the old movies are not linked. That's why. So I should have checked it before I brought it here. But that's totally okay. So here, what you're going to see is that you have all these fibers, and as you're deforming them, initially all these fibers bend. Then actually they start stretching, and when they stretch, all these fibers align along the direction of stretch. So that's really what's going on. And I do remember a talk that I gave recently from this one at the University of Minnesota. Yeah, this one should work. Not quite. Oh yeah, that's right. That one. Okay, very good. So you see now when you deform this material, a lot of these fibers that were perpendicular to the direction where there is high tension, so I'm shearing this material. So as I'm shearing this material, what's happening is the fibers that were in the direction, this 45-degree angle, all stretched, and the ones in the perpendicular direction actually buckled, okay? And so there is this phenomena that actually gives it the nonlinearity, nonlinear character. And to see why that's the case, here I have, I have plotted here you can see these plots. As you're increasing the shear strain, these fibers are getting aligned. And when you shear it further, the only way you can further cause deformation by stretching the fibers. So low levels of deformation like this, fibers can bend. High levels of deformation, the fibers have to stretch. And bending is easier than stretching. It is for that reason that this material strain stiffens, okay? And you can see that also in tension. If I apply tensile stresses, here you have a bunch of random fibers. When you pull it, you see all these fibers align. And further deformation really requires stretching of these fibers that were initially random but now are aligned. So the point is, if you take only linear elastic materials but cross-link them and align them, that can actually impart nonlinearity to the material, okay? So that's nonlinear elasticity. And this sort of phenomena works, of course, for collagen. That's actually collagen. And when you align is where here the material is soft. As you increase the stiffness, it becomes stiff. As the deformation, it becomes stiff. And you've heard a lot about actin. These are actin networks, and this is the elastic modulus versus the stress. And you see they also show this behavior where initially the material is soft, then it gets bigger. It also depends on what I call molecular motors. The details are not that important. And here the nature of the crosslinks is also important. If the crosslinks are rigid, the material will be stiff, otherwise it will be soft. So that's another set of experiments showing that the material is nonlinear, and putting in molecular motors can change the behavior, all right? So that's the first class of materials. Now let's go to the second class, what I call viscoelastic materials. So this is where the crosslink dynamics is going to come in, all right? So here, yes, any questions? Yeah. For sure, for sure. But it's a matter of time scales. It's a matter of time scale. So when people are doing this shear rheology measurement, they're oscillating it really, really fast. So the question is, on those time scales, can these enzymes change the properties? Some enzymes can. Some enzymes can. So there's aging and things like this. So the collagen network over a period. So I'm just giving you a snapshot. I'm just telling you, take this material and you deform it and you test it. This is what you will see. But in your body over a period of time, right? Your ECM and my ECM are very different. I'm way older. Mine's going to be softer. Yours is going to be stiffer. All right. So aging is a very important thing. Enzyme. That's why biology is fascinating. Over a period of time, you have all these changes. that are going on. I'm giving you a snapshot. So all of these properties that I mentioned have to be, you have to attach a time label to it. Okay, and time label, many things are happening, you know, depending on what your level of physical activity is, what you're eating, and all these other things. That's a very good question. So we are only looking at a snapshot and describing it over a time scale of your measurement, but other things can happen over time, and that's the whole area we are really interested in. You know, how do the systems evolve? That's a very good question. Same with plants. You're a plant biologist. As a plant grows, you know, the cell wall stiffness is going to evolve also, right?
This just reminds me of like what the chlorophyll microtubule network in plant cells, because the cells are young, they look more randomized, but then as they expand, the chlorophyll microtubule becomes parallel in order, and that just like looking at the shearing or the strain that you're showing and how they become more aligned, it just kind of seems like a parallel.
Oh yeah. So alignment, ordering, all those things can take place. Could be due to strain. Could be due to strain accumulated over a period of time too. So there's a time variable as well. That's a very excellent point. All right. Okay, other questions? If not, let's look at the next sort of class of response called viscoelasticity. So here I have fibers, or you could even think of these as polymer chains if you want to. Okay. So in a lot of polymers, these polymer chains are cross-linked. A cross-link is basically a lock and key. Okay, the cross-links can be on, they can be off. So there's some kinetic, some dynamics to it. The previous slide, I ignored this dynamics because in collagen there are what are called covalently cross-linked, there are a lot of covalent cross-links. Covalent, anyone knows example of a covalent bond? Like a silicon-silicon bond is covalent. It's whatever you do, it's not going to break. But there are much softer bonds that can form and break and reform. Those are the things we are thinking about here. Okay. So here, so the point is it's a lock and key mechanism. And in the absence of strain, basically there's an energy landscape. The lower energy is when the things are attached, and the higher energy is when they are detached. But any given point of time, like like you mentioned, things can be coming on and off. But again, here we are not talking about years. We are talking about seconds or minutes. They can come on and off. Okay. So this kind of a behavior will have a significant impact when you deform this material. Okay. When you actually deform this material, is there a pen here, Jim? Yes. So what I want to draw here is, this is basically what people call reaction coordinate, meaning the amount of stretch in this. You have an energy landscape like this. When you deform it, basically, so this is when this curve that I have is when force is 0, no applied force. Okay, this is when F is 0. Now when you apply a force, what's going to happen is that this configuration can become lower in energy. That's why the material is going to stretch. A stretch configuration will be lower. Okay. But then you need to remember that, so here you're in the sort of on state, if you will. Here this is on, that's off. But then there is an energy barrier the system has to overcome to go from the on to off. I'm sure you've taken many chemistry courses. It's a common phenomenon in chemistry. There are two states. To go from one state to the other, you got to overcome an energy barrier. Now this has very important implications for mechanics. So let me tell you give you an example. So, and I'll show you data in a second. So if you apply a step deformation, meaning right now the material, I'm not deforming it. This is my, let's say that's my rod, a test rod, no deformation, and then I'm pulling it all of a sudden, and then I'm keeping that strain fixed. Okay. Then what I'm monitoring is how much force do I need to keep the amount of deformation fixed. So in a viscoelastic material, the force, initially you'll not apply a large force, but that force will decay. Okay. If I do the opposite thing where I keep the force fixed, how can I keep force fixed? Just hang a weight, force is fixed. Then what's going to happen is that material is going to do what's called creep. It's initially it looks stiff, but with time it actually starts deforming more and more. And that's called creep, this is called stress relaxation. Both of these actually follow from this concept of the cross-link dynamics. Let me explain how physically, just going back to the previous slide. So imagine that I took this material, I applied a certain amount of shear and kept that shear fixed, meaning I deform it like this and keep the deformation fixed. Then what I'm trying to figure out is how much force do I need to keep that level of deformation. As soon as I pull it, none of these crosslinkers are broken. So basically, you will get a high stiffness. But with time, it prefers to be in a lower energy state as a function because you applied a force. So some of these crosslinkers would want to break, but they can't do that right away because it's an energy barrier. So it takes time for them to break, okay? And as they break now, your material is softer because you don't have to deform as many crosslinks. So that's the reason why you get this, why you get the relaxation of the force. By the same token, when you apply a fixed amount of force, it will now deform more because as I apply this certain level of force, your crosslinkers are stiff. As they break, the material will deform more and more. So both creep and stress relaxation follow from the same concept, which is the fact that it takes time to break these crosslinks. Okay, is this clear? What I said? Yeah.
So you impart an energy into the system.
Yeah.
Break crosslinks. Over time, the system adjusts to reform those crosslinks at a different configuration.
That actually has to do with plasticity. I'll come back later. So here the assumption is that the number of players are fixed. You have certain number of crosslinks. You're not really deforming the heck out of them. It's only a small deformation. Okay, once you do larger deformation, I'll come to that later. So fixed number of crosslinks. The number of crosslinks are fixed, and that works in many situations. Now I'm deforming it, okay, and giving them the chance to break and reform both. But as you are actually applying a force, the equilibrium moves more towards the broken state. Means it gets softer, but it takes time to get there. And that's the time scale you're seeing of relaxation. Bringing in newer crosslinks, that's a new concept. We'll have to go back, that's plasticity, okay? So the thing is, I'm glad you brought this up because a lot of books, I'm going to show you the next thing what's done in books. They give you a bunch of equations. But what people miss is this fundamental concept, the physical picture in the back of the mind, okay? So in many ways, this sort of a time dependence is actually similar to what fluids do. When you shear, when a fluid flows, there are layers that are actually shearing. It's the same concept. There are bonds that are actually breaking, then they are reforming. So fluid is actually a sort of there's plasticity in it, but there's viscosity as well. All right, so these two concepts are different and we have to distinguish them. I'll come to it, hopefully there'll be time. All right, so the way these things are described is that if you have a solid, the stress is proportional to strain. If you have a fluid, I don't want to touch fluids because Dan is going to do that next lecture. Fluid, the stress is not proportional to strain, but stress is proportional to strain rate. It is not how much you pull, it's how fast you pull. That's what a fluid is. And these materials, because the fact that there is this on and off, if I pull it very fast, there is no opportunity for these crosslinks to really unbind. It behaves like a solid. If I pull it slowly, the crosslink can unbind, it becomes softer. So that's the whole idea, all right? And there are many models that you can use, there are models where a solid is a spring, a fluid is a dashpot. And you can arrange the dashpot in many ways. You can arrange many of them and so forth, and there are these models. And I don't want to go into the details of the math, but it's there. By the way, so Jim, are we putting these slides somewhere for the students to? Yes. Yeah, so you can look at these at your leisure, and it's also available everywhere else. So now let me show you some real experiments where you can measure this. So this here is a collagen fibril, okay, meaning previously I showed sort of a network of these. But if I look at individual one of them, okay, it's a MEMS device where you can sort of hold these, collagen fibrils and then do exactly the two tests that I said. First is you basically pull it, let it be, let it stay there and see how much force you need to hold it. The second experiment, you apply a fixed amount of force and see how it deforms. You can do those experiments. And if you do that, then basically what you get is this. You see exactly this strain relaxation, okay? And then you see creep. The material is, is deforming more and more. So when I told you about that one crosslink, there was one time scale, but there could be multiple crosslinks. One kind of crosslink, a second kind of crosslink. Each of them will have its own time constant. So the model to describe it is some backbone elasticity and two different time constants. And here, you can look at it. These time constants are given here. They are of the order of 1 8 seconds, the other 100 seconds. So you see here there is a really fast relaxation, then a slower relaxation. So maybe one of the crosslinks actually breaks really fast, but the second type of crosslinks are then breaking slowly. Okay, so it kind of gives you insights into the physics. There could be many relaxation mechanisms. And if you know what a glassy material is, you've heard of glasses, and glasses are very different in their time-dependent response than like an elastic solid. A glass is a material that's got all relaxation time scales. Means not just one or two, all. Okay, and aging and all that is related to that. Aging of glasses. Okay, so you can have many of these processes, but this is the concept. The concept being it takes time to actually break the crosslinks. Okay, all right, very good. So that's a collagen fibril. You can do the same thing with the tissue. So this is basically an experiment of a stress relaxation experiment where they took this is a heart sample, that's a limb bud, liver, neural retina, all of these materials. You see that the force actually as a function of time relaxes. And again, here too there are two time scales. And one of the time scales is about 2 seconds. The other time scale is about 10 seconds. So typically, most biological materials, whether it is a building block like a collagen fibril, or the tissue itself, or the cell itself, typically has a relaxation time scale of the order of a few to 100 seconds. Okay, so instantaneously it has some elasticity. With on time scale 100 seconds, that elasticity will get softer. Okay, so that's the concept. Okay, so now I'm going to the next one. Okay, yeah. These are tissues. These are tissues. Yeah. All right. So the next concept I want to touch upon is poroelasticity. Okay. So here, in the first example that I talked about the fiber network, and in the second example that I talked about this network with crosslinks, there was no fluid. But any biological material, as I pointed out earlier, has fluid in it. Okay. So the common example is a sponge. Sponge is basically an elastic solid that's connected by pores. When you immerse the sponge in water, it will basically soak water and it will swell. Okay. Though I'm going to show you in a second, biological materials are very different from sponge for a very important reason. Okay, but sponge is a good thing to sort of keep in mind. Now, when you take this sponge that's soaked with water and squeeze it, meaning you apply compressive stress, fluid flows out. Okay, and this sort of fluid-filled solids are what we call poroelastic materials. Remember, the solid is still linear elastic. Okay, there is no viscosity, though it can be viscous also, but it's an idealization. Okay, so you have a solid material like the ligaments of a sponge. And if you can soak water, and that's poroelasticity. And so elasticity of fluid fills porous solid is also called poroelasticity because the solid is porous. Okay, and again, because all biological materials, including cells, tissues, ECM, all of that has fluid. Without fluid, there is no life, right? So they also have to be poroelastic. Now, question to you: where did this theory first start? How did people start thinking about this? They started thinking about it actually in consolidation of soils. You think about concrete, you start to think about building materials, there's also fluid there. So the mathematics of this was developed in the 30s and 40s in the concepts of, in the context of soil mechanics. But then, since it has been used to gels, biological tissues, lithium-ion batteries, that's a place where this applies. Okay. It also applies to like hydrogen storage and things like this. So this concept is actually not just a biological concept, it's of much more broader applicability. So let me go into sort of explaining the physics here. So the question is, so let's say, let's ignore the text for now and just look at what's at the bottom. Imagine that you had a polymer. So this here is a polymer, okay? Polymer, if in its normal state, usually will be coiled. Why? Because of entropy. Okay, so you take a chain and the chain can assume all kind of configurations. A straight configuration you can only hold, you can only have that one way. All the atoms, all the bonds stretch. But if the bonds are all kind of rotated relative to each other, they can actually sort of curl up. Okay, so polymer, because of entropy and a curl configuration, there are many ways of doing it. So the entropy is large. So for entropic reasons, the polymer will be coiled. Okay. But you take this polymer and put it in a solvent. You did polyacrylamide, so there's a polymer chain there. When you put it in water, it actually swells. Okay. So first thing, before we understand the mechanics, we have to understand why is this thing swelling. That's the thing you got to understand. Okay. So it's a competition between a number of different factors. The first is actually the elasticity of this backbone. Of course, now if you dry it, it will go back. Water will go away, your fluid will go out, and then it will come back to where you started from. So very quickly, so it's actually a competition between various factors. The first is basically, so I have the text here. So when a network swells, basically two things happen. You're actually, this network wants to be in this configuration, but you're stretching it. So that's the cost. Okay. Every time when you have any kind of physics, it's always a competition. There's something pushing it one way, something pushing the other way. The balance is where we are at. And that's true in life too, right? I mean, it's a general concept. Everything is sort of a homeostatic equilibrium. So here, you look at this, it's actually deformed. But then, where is the gain? Once the fluid gets in, the polymer is deforming, no good. The polymer in its natural state wants to be coiled. So where's the gain? The gain could be multiple places. There could be sort of hydrophilic interaction between this and the chain. So as you stretch it out, more and more water molecules can access the polymer. So that's the hydrophilic, there are hydrophilic and hydrophobic interactions. So that could be a gain. The other gain is actually configurational entropy. Okay, so if I had, if this polymer was coiled, when you uncoil it, you're losing the entropy associated with the fluctuation of these. But there's also configurational entropy, meaning the mixing entropy between the water molecules and the polymer. That actually goes down. Okay, and there is a thermodynamic driving force for swelling. All right, all of this you can change in multiple ways. You can change the kind of residues on this polymer, change the hydrophilic interaction. You can change the stiffness of these networks. That will change this. A lot of different things. Okay, so when people are designing different hydrogels, they are changing the mean distance between these crosslinks. They are changing, the individual stiffness of these things, and various factors like that. All of these things collude to basically give you a swelling. So this here is a polymer gel. That was then put some fiduciary maybe some tracks where there is ink, and now you see that it's swelling, but it's taking it time to swell. Okay, so when you have this polymer gel, and you put it in water, it's swelling. Okay, and it's taking time. Why is it taking time for this polymer gel to swell? Yes. So here, there is also a time scale, but it is not the time scale for this crosslinks to come on and off like the previous case. Here it is associated with the time scale for the fluid to flow. Okay, so that's what's giving this a time scale. Okay, and diffusion is a frictional kind of process. When fluid is flowing in and out, there's dissipation. So this is also a dissipative process having to do with how fast water will flow in and out. So there are many applications of hydrogels. So now let's look at, so I gave you two concepts here. One concept time scale associated with the fact that you have crosslinks breaking. Second concept being when I deform something or when I swell something, it takes some time, but that's related to time scale of flow. Okay, so these are two different time scales. And as Alex pointed out, it is diffusion. Okay, so that concept is going to come up in a very prominent way in a second. So now let's look at some experiments. So this is actually some work my friend Kristen Myers, who's at Columbia, this is her work, of the mechanical response of the cervix. So here, so that's the cervix. What she does is, she's interested in understanding the, giving birth is a very complicated thing. There's a lot of mechanical stresses and things like that involved. So she's very interested in understanding why some women have difficulties giving birth and the mechanics associated with childbirth basically. So here she takes she gets samples from mice, from animals, as well as some human work also. So with this she punches out some samples, and here what she's doing is she's taking that sample and 3 different sets of experiment. So here everything's in a fluid bath. A tissue cannot survive without fluid. Okay, so that's her sample, and she puts it between 2 plates, and then she's doing a load-unload cycle. She's loading it, unloading it. Okay, like that in a triangular pulse. Basically, do that. And here she's actually doing. So here the net level of strain is the same. Here she's actually increasing the strain, keeping it constant, doing that. But again, there's the fluid. Here is different. She's actually put it in a in a container where the fluid cannot flow sideways. It can only flow vertically. So these are 3 different sets of experiments. And this here is your strain. All 3 of them are strain because you're doing this. You're controlling the displacement. If the material were linear elastic, what would the stress here look like? That's what I'm going to plot next. What would it look like? Simple answer, right? It's a linear material. A triangular pulse has to be triangular also. Slope will depend on elasticity. But let's see what this material is going to do. She's actually, so yeah, sure. If this were a linear elastic material, right, there is time, but instead of, where did I leave the, yeah, instead of time, if I plot strain here and stress here, if it is a linear elastic material, how will it look like? It'll basically be a straight line, right? It's going back and forth along this line, basically. That's what it is. Now, because this is a nonlinear material, we'll answer the question of whether it is viscoelastic or poroelastic in a second. That's really the goal. If you look at this, then this is what you see for different, these are different samples. Non-pregnant, no previous deliveries is this. Non-pregnant, previous deliveries is this. Pregnant but taken a cesarean section is that one. So 3 different physiological states, if you will. It's not really following a straight line. It's actually doing much more complex things with more and more load. The important thing is that when you load it and unload it, they don't follow the same path. There's dissipation. First thing to notice. Clearly, there will be dissipation in viscoelasticity. Why? When you break a crosslink, there is energy stored in that crosslink. You're breaking it. Where does that energy go? As heat. That energy is it's dissipated to the fluid surrounding it. So there will be loss. So when you go take the stress strain curve, there will be hysteresis or energy loss. The area under this is the energy lost. Okay. In poroelasticity too, there will be, because the water came in, to flow the water in, you do some work. When it goes out, you do some other work. You do work also. Okay. And there is dissipation in this whole process because diffusion is viscosity. So you're going to dissipate water energy. So both these processes will dissipate energy. Okay, I'll come to which is what in a second. Now let's look at this case. This meaning either one of these. Let's say the first one here. This one. So here, if you plot the stress strain curve, here what's happening is I'm ramping the load, so it's going there, and then I'm holding it there. When I'm holding the deformation there, if it's an elastic material, the force will stay where it is. But here you see stress relaxation. Here too you see stress relaxation. Both the viscoelastic material and poroelastic material will show stress relaxation, because for a poroelastic material, if I squeeze it, right away the fluid has no time to flow. As I wait there, the fluid will flow and the material becomes soft. You had a sponge, you boom, sit on it, right away the water cannot go out, right? I mean, it takes time. So that's the reason. So in both cases you get stress relaxation. And the question as mechanical folks who are analyzing mechanical responses, which is it? Is it poro or visco? That's really the question. But both show similar behavior, okay? So that's basically what it is. This is the confined and that's the unconfined. Distinction being that in one case, you know, the fluid flows this way, the other case the fluid flows the other way. Yes?
Does it, in the first compression, is it more poroelastic, and then as you lose water, it becomes viscoelastic?
In this case, I'm going to come to it in a second. Yeah, I have 10 minutes. But overall, in this case, analysis shows it's poroelastic. But what you say is perfectly plausible. Okay. So yeah, so what we need to do is both of these phenomena really require sort of an understanding of what the dissipative mechanisms are. So I have only 10 minutes. I'm going to show you a couple more slides here, a few more slides. But I want to touch upon a little bit of math. Now, for a simple viscoelastic material, there is some time scale. Let's call it tau v. Some viscoelastic, some time scale associated with breaking. Now, as you correctly pointed out, for this poroelastic material, there's a diffusion constant. Okay, what's the dimension of a diffusion constant? What's the length time? What's the dimension of a diffusion constant? No, diffusion constant is meter square per second. Okay, very important. Important everywhere in any field you are, any science field you are. So this has got dimension of meter square per second. Okay, that's a diffusion constant. Okay, maybe Dan will. It's an important concept in fluids too. Maybe Dan will touch upon why it is. But let's just take it like that. Now, if your sample size is L, so this is your diffusion constant, and this is your sample size. Okay, so L square divided by time then is diffusion, or the characteristic time scale for this relaxation is L square divided by D. Okay, that's the characteristic time scale for relaxation. If your sample is small, fluid can flow out fast, it will relax fast. If your sample is big, the time it will take, you understand this equation? I don't know if you can see it also. You can, right? Yeah. So the time is L squared divided by D. L is your size of the sample you're testing, and D is the diffusion of water, diffusion constant of water. So it turns out that to figure out whether the material is responding to viscoelasticity or poroelasticity, what you need to do is you need to actually plot the characteristic viscoelastic time scales. For cells, I told you that it's between 1 second and 100 seconds. So for cells, it actually is here. Okay. And then maybe let me write this here so everybody can see. So I told you that the tau is actually L squared divided by D, the characteristic time, or I can write the size is like tau D. Okay, and so here, here if I plot D times the tau, there is a particular size scale you will get. So depending on where you lie on this curve, it can be viscoelastic or poroelastic. So let me explain that here. There's a bit of math involved, so maybe I'll just show it to you here. So I'm taking time, I'm dividing it by the characteristic viscoelastic time scale, no dimension. So that is this dimensionless number. If the material were poroelastic, this is your characteristic poroelastic time scale, which is L square over D. And then to make it dimensionless, I can plot it as this, and that's this axis. Okay. Different materials will lie at different points here. Yes.
So what L is not the total size of the sample, but some unit size within the material?
L is the size of the sample. or size of the region you're loading, because you need to expel the fluid from a region of size L. Okay, it's not a characteristic size of the material, it has to do with the size of the sample. Okay, okay, all right. Yeah, okay. So the point is, here what I'm plotting is L squared divided by D, which is the poroelastic time scale, and this is actually your actual time. So if you ignore this, if your time scale is much bigger, you know, if your time is much bigger than the viscoelastic time scale, viscoelasticity is relaxed if you're here. If you're here, viscoelasticity is unrelaxed. Meaning, so viscoelasticity, if you're looking at time scales much smaller than the viscoelastic relaxation time scale, the material looks elastic. If you're looking at time scales that are bigger than the viscoelastic time scale, the material will be softer. So viscoelasticity can relax or not relax depending on where you are relative to this side of this line or the other side of the line. Okay. For poroelasticity, you have this L squared divided by D. Okay, you have L squared divided by D. If your if your sample is very big, if the sample is huge, irrespective of how much time I wait, water cannot flow out. Okay, so in that case, poroelasticity will be unrelaxed. So above this line, poroelasticity is unrelaxed, and below this line, poroelasticity is relaxed, meaning the fluid can flow out. Okay, so now you have the basic poroelastic time scale, basic viscoelastic time scale. You have these two lines. So if I draw two lines, how many quadrants? Quadrant means 4, right? It splits the whole space into 4. Okay, and depending on where you are on this space, if you are here, if you are crossing this line, you are looking at poroelastic relaxation. If you're crossing this line, that's a little complicated because you're seeing both viscoelastic and poroelastic relaxation. If you're crossing this line, then you're looking at viscoelastic, and so there are 4 combinations. If I write RU, how many ways can I arrange R and U? RR, UU, UR, and RU, 4. So those are the 4 things. So the point is, depending on the time scales you're looking at, depending on the size of the sample, you can either be looking at poroelasticity or viscoelasticity. And that's sort of this phase diagram where you see this. Okay, now I have no time to talk about plasticity, no time to talk about active models. So I'm just going to very quickly go through different experiments and show you same cell, but people are doing different measurements. And depending on the measurements they're doing, you are in different regimes here. Okay, so that's what we want to see. All right, so just very quickly, without looking at the board, what's the time scale of poroelastic relaxation? Look at me, not at the board. Abby. Very good. And the time scale of viscoelasticity is an intrinsic time scale. We don't know what it is. Okay, it's a competition between these two. So if I test bigger samples, will I be looking at poroelasticity or viscoelasticity? Poro, because bigger the size, more time it takes for the fluid to flow. So you will be looking at poroelasticity. Okay, all right. So let's look at a few experiments. So this experiment, there is a cell, and these folks, this is a Nature Materials paper. Sorry, I don't have the reference here. So actually, we are now working very closely with the first author of this, Emad Mudaberry. He's at University College London. So these are some experiments that he did, where he brought in this cantilever here, and he poked the cell, and he looked at time scales of the order of 0 to 0.5 seconds, less than a second. And clearly he kept this, this is the bead. He basically brought the bead in, and the main curve to focus on here is this. You basically see the stress relaxation. So if you go back to some of the things that I mentioned, we have this L square over D, which is your poroelastic time scale. That turns out to be, if you put the diffusion constant of water, it turns out to be 0.1 seconds. So here, and the viscoelastic time scale for cells, I mentioned it before. What was it? 1 to 100 seconds. That's the typical time scale. And here he's looking at processes on very short time scales of 0.5 seconds. So this really has to be poroelasticity, because the viscoelasticity has no time to relax. It takes more than 1 second. So this here is a poroelastic. This here is measuring poroelasticity. But you do the same. You do a similar experiment This is work from Farsh Gilak. And here he's looking at force, same thing. Bring an AFM, go to a cell, poke the cell, and see how the force relaxes. Right away, if you look at that curve, okay, you can clearly see something really fast is going on here. Okay? And then subsequently, there's something going on also. So this very fast relaxation has to do with poroelasticity. But the subsequent relaxation on this time scale, you can just put those numbers I told you, is actually viscoelasticity. So on bigger time scales here, you're seeing viscorelaxation because the size of the indenter and so forth, if you know, and that's basically what you're seeing. Now let's go to some of the other experiments. So this experiment that I showed you before on the on the properties of this embryonic tissues, it was a tissue whose size was like 100 microns. Okay. So if I now put L square over D, D is basically roughly the diffusion constant of water, okay, you get 1,000 seconds. Whereas the time scale that they measured is about 10 seconds. So this is actually the viscoelastic case because this time scale is bigger than that. In the sense that the poroelasticity has no chance to relax. It's because of the fact that your size is 100 am I saying that correctly? L square over D, maybe 100 microns is 10 to the minus 4, right? Yeah, so this here is viscoelastic, and I had an example here that this example actually is poroelastic because the time scale here are thousands of seconds. So this here is poroelastic, and here the size was 1 millimeter, so that's right. So when the size is big, you measure poroelasticity, size is small, you measure viscoelasticity, okay. So, so out of the laundry list I had, I didn't go very far. I did the hyperelasticity, I did viscoelasticity, I did poroelasticity. The other concepts have to do with plasticity and an active material model. So it's in the slide, so no time now, but take a look. But just understanding these three is quite important for further work on mechanics of tissues, cells, ECM, and everything else. Yeah, I'm kind of exactly at 10 o'clock, but maybe a couple of minutes for questions, if there are any. Yeah, sure.
But early on, you had a slide about the leaky junction, about the cancer travel.
Yes.
What is that about, the leaky junction?
Oh, leaky junctions? Yeah. So it's sort of unrelated, but basically what happens is when you have these junctions between epithelial, two cells, then there are these bonds called cadherins that actually these are adhesion molecules that hold the two junctions together, right? And these junctions are also pulled because there is some actin, cytoskeleton with motors and things that are pulling. So basically, depending on the level of contractility, these the force may be enough to sort of pull these apart. Okay, and cells and tissues have ways of regulating this contractility. So a lot of times, the blood vessels around tumors tend to be leaky because what ends up happening is there are all these signaling mechanisms where the contractility is altered, and so the blood vessels can be leaky, and then the cancer cells can escape through them. So that's something we're working on also, and there's interest in the center on that. Rick Asoyan, he does a lot of work on that if you want to discuss further. Right, so, but that's, in this context, it's basically the whole thing is viscoelastic. It's turning on and off, the junction is. All right, very good.